Does anybody have homework questions? Yes.
4.4 or 4.5, I believe I can confirm. 4.4, 5. 5. Oh, sorry.
4.5.
No, the 4.4, then 5.
Oh.
5.
Okay.
I said 4.5 first, but I didn't remember.
4.4, number 5.
It's about symmetry, scale. Symmetry scale.
So each of these has symmetry of scale. You see, this is the plain tile, and then we make a super tile from it. So if I use the one in the bottom left, I can make 4 copies of it to make another one like this one, only larger. So there's 4 copies in the super tile, and then the next biggest size I can make uses 9 tiles. So the next biggest layer has these 4 plus 1, 2, 3, 4, 5 more to make 9. So the super tile has 9. And that's the same for this one as well. So this triangle is the tile, and I can make another triangle this shape using 4 tiles. Or I can make one using 9 tiles, but I don't think they have a picture of that here, really. Let's see. So I'd have to take these 4 more and then put one on the top right here. And that would make 9 tiles into a super tile. So this one is 4 and 9 as well.
Wait, so how? Never mind.
So 4, or if you take these 8 and put one on top, then there's 9. Any other questions?
I don't know what the question, the real life example, I don't remember what it was.
Oops.
18, mine's 18.
Yeah, so this one I think is harder to see. So symmetry that shifts every point to the right. So I think they all do that. Like if we pick this up and move it over, it lands here. And if we pick this up and move it over, it lands here. Same thing for this. If we pick this up, it looks like these two. We pick these 2 up and move it over here. Transparency would help us to make sure we could do it exactly right, but I think it is all of them. So they can all be shifted right. These alternate, right? Candy cane, zigzags, candy cane, zigzags, candy cane, zigzags. So we just shift everything to the right. It should be lining up. So right half and left half flip. So you can flip this one. Maybe we flip this over itself. Well, that's the bottom one, flipping the frieze over. Flip the right and left half. So the right and left half are the same here if you divide down the middle. This one's not, though, because here the little, well, look down here, they all point to the right. These little, like, they kind of look like dog heads. They're all pointing to the right, and if we were to flip it, then they'd point to the left. So that doesn't work with a right and left flip. So I'm going to focus on these little hooks that come down to the right. You see how these little hooks come down to the right, but they don't ever come down to the left, so I can't flip that one either for left and right. But these I could flip because it's just every other one, every other one. So if I flipped it left to right, it would still be every other one. So number 1 and 4, flip left and right. And that's the same with actually flipping the frieze over. So if we flip it, like if this was a transparency, and I wonder if he means vertical flip. So if he means a vertical flip, or if you're flipping it over, number 1 works for that, because the top and the bottom half are the same. And number 4 works for that. So the top and the bottom half are the same as well. There's this little kind of perspective thing going on, but if we had this extended taller throughout the plane, then I think that would be unaffected. So that's 1 and 4 as well. Whoops, that's not it. 1 and 4. Whoops, where do you see the check mark or whatever you got? Yeah, green. Green means good, right? Okay. What other questions did you have? Then let's go on to 4.5, the platonic solids. So as we look in the platonic solids section today, we'll be watching for coincidences. The life lesson here is that coincidences are flashing lights, alerting us to potential insights. So later on, we'll be watching for coincidences. I wanted to just read a little bit about what brings the platonic solids to the interest of people through history. So from your textbook, we read that for centuries, the platonic solids were associated with mystical powers. Even though the great Greek mathematician Euclid wrote about the regular solids, they are named after Plato because he apparently attempted to relate them to the fundamental components he believed made up the world. A little glare on there. Let's see if I can take that off. Okay. Who knows, what are the fundamental components that make up the world? What would Plato have been thinking about? What would they be?
Fire, water, earth, air.
Yeah, fire, water, earth, air. I'm not sure what he did for the 5th one. Has anybody heard of what people might suggest for the 5th one? I'm not sure what that was.
No, is it
Ether? I think that might be air though, or light. I don't know what it was. But Johann Kepler shared this sense of awe for the platonic solids. Although Kepler is remembered best for his laws of planetary motion, he was proudest of his book, Mysterium Cosmographica. In it, he proposed a theory to explain the structure of the solar system. At the time Kepler lived, there were 6 known planets. Kepler showed that it was possible to take the 5 regular solids, put one inside the other, and have the sizes of inscribed and circumscribed squares about those solids reveal all the sizes of the orbits of the planets. So Kepler did a lot of work with planetary motion. Well, we're looking at the platonic solids together, so hopefully you have yours and you can take them out. And we'll look at them one by one here and watch for coincidences. I'll turn the light back on so I can see. So your simplest one, these are, we'll go from simplest to hardest. Here's the one that's made up of triangles. And I had asked you on Friday to think about the one made up of squares. We only have one that we made composed of squares. I had asked you to think about what were the possibilities of how many squares could meet at a corner. So the cube has 3 squares meeting at a corner. The corner is called the vertex. Could you make a solid with 2 squares? A regular solid. Regular solids are the same as platonic solids, so I'll use those words interchangeably. Could 2 squares meet at a corner? to create a regular solid? So think about what that would look like. If you had not made yours yet, maybe you could think about what that looked like as you were making it. Did anybody come to a conclusion about having 2 squares meeting at a corner instead of 3? Yeah, could 2 squares meet at a corner to create a regular solid? So 2 squares meeting at a corner. Now they would share an edge, or else they're not going to make a solid at all. So if you have 2 squares meeting at an edge, could you take other sets of 2 squares meeting at edges? I mean, two squares meeting at a corner and make a solid out of those? So if you have 2 squares meeting at a corner, it's kind of like a door, right? A door on the wall, a door in the door frame. There's really not another way to get another square there if you think of that like a door. There's really not another way to get another square in there unless, in fact, you put 3. You can't make a solid with just 2. How about 4? So we're thinking about how many platonic solids there are, and so we're thinking about, as you construct them, how many are you going to put together? So we have these just handed to us and with little pictures saying, here, make these. But the people who made them didn't have that. The people who made these millennia ago were thinking, well, how many squares can I put together here? How can I construct this? 3 works. Could you do 4? Anybody? What would happen if you had 4 squares meeting at a corner? We'll draw it on a piece of paper once. Okay, you have 4 squares meeting at a corner. So we couldn't put 2 squares together and get a regular solid from that. Okay, we couldn't make a shape that had all the same size faces, regular polygons, and the same number of faces meeting at each corner. We couldn't get a regular solid with 2 sides meeting at a corner. What about if you had 4 squares? Could you form that into a regular solid? What does it look like? I mean, it just flattens out, doesn't it? Because you have these 4 90-degree angles, and they flatten out. So 3 fit together beautifully. You have the 2 that make like a door frame, and then the third one fits on top. But if you put 4 on there, you're trying to squeeze 4 in to meet at a corner. Well, all of a sudden, they have to be flat for that to happen. So no, you can't get a regular solid with 2 squares meeting at a corner or with 4. So those are the kinds of things we think about when we're thinking about how many platonic solids are there. Look at the platonic solids you made with triangles. This is the tetrahedron made with triangles. So these are all equilateral triangles because they're regular solids, so they have to have the same polygons, regular polygons on each side, and that means equilateral polygons. So equilateral triangles. So three polygons. In this case, triangles. 3 triangles meeting at a vertex. Or you had the octahedron. So at every vertex on your octahedron, look at your octahedron. How many triangles are meeting at each corner there?
5.
This one is the. Yeah, you're ahead of me. No, that's good. How many meet on the octahedron? 4. Yeah, 4 are meeting at every corner. And then you just said this one had 5, which it does. This is the icosahedron. So we had 3, 4, and 5. 3, 4, and 5 triangles meeting together to make these regular solids. Could we meet 6? Okay, so these are all equilateral triangles. Could 6 equilateral triangles meet together at a vertex? Could 6 equilateral triangles meet at a vertex to create a regular solid? So again, we're looking at regular solids. Same regular polygon for each side, and same number of polygons meeting at a single vertex. Well, let's draw it out. Does anybody know how many degrees are in each of these angles in an equilateral triangle? Anyone remember? So equilateral triangle, all the angles and sides are the same. So how many does that make? 180 total and 60 in each corner. Yeah, 60. So if there's 60 degrees in each corner here, how many degrees have you made in the middle there? You've made 360. How many degrees are in a circle? 360. So again, just like with the 4 squares, you've collapsed into flatness. So 5's the most we can do it with these equilateral triangles without degenerating into a flat plane instead of having a three-dimensional shape here. Well, I'd like you to work on quantifying these parts and looking for coincidences while you're doing that. So please take all your platonic solids and we'll make up a little chart. So we'll list the solid on the left here, the tetrahedron, and this is something that we'd have on the quiz, so make sure you get this filled out right. Tetrahedron. What does tetra mean? Does anyone know what that prefix tetris means? 4. Yeah, 4. Tetrahedron, 4. Good. Cube. Octahedron. What does octa mean? 8. Yeah, so 8 sides on that one. Tetrahedron has 4 sides. Dodecahedron. So I'm putting these in with increasing number of sides. They're called faces or sides. So dodecahedron, dodeca is, who knows what dodeca is? 12. Yeah, good. Dodeca is 12. Icosahedron. What does the icosa stand for? Anyone know? 20. Yeah, good. 20. Okay, so we're going to make a chart. We have how many vertices? Number of edges. Number of faces. Number of faces per vertice. Number of sides per face. I'll make that a little bigger. Okay, so how many vertices, number of edges, number of faces per vertice, number of sides per face. So go ahead and work on yours and fill this in. If you didn't bring yours today, ask the person next to you to look on theirs. And I'll come around and see how you're doing. You can also come up and borrow mine if you bring them back, then one at a time, okay? Okay, so you can borrow a couple of those.
You feel a little more.
It did, but
That's the one that I got done?
yeah, I tried fixing it.
So you have yours with you?
Yeah, just my bigger ones.
Your bigger ones fell apart too. Okay. Okay, you have yours with you. Okay. Do either of you have yours?
Yeah, I have one.
Okay.
I have a program I'm looking at.
That's cool.
Has yeah, so at home I have.
Oh, the other ones?
And this,
Faces per vertice.
you just want a picture, right? You don't want to hand them in?
Right.
Okay.
That's your list. This one's the hardest. And then you didn't bring yours, you brought pictures of yours. Did anybody in this room bring anything? You have pictures of yours too? Okay, that might help then.
Plus this counts. Yeah, so that'd be 1, 2, 3. Yeah, but it's number of faces per anyways.
Well, if you haven't made yours yet, the cutting into 4 seems like the way to go. And then this, so you have yours.
Yeah, they're on the bottom.
Okay, but that's what yeah, but not for the you gotta send them. But you have
Yeah, I have them. I lost them Friday. I forgot to bring them today.
Yeah, so if you didn't bring yours today, Wikipedia has it.
This one.
I think that one, oh yeah, that one worked. That one falls apart the easiest. It's so weird. It's just not a stable structure.
Those reactions.
That's what mine is.
What exactly classifies as the side?
So the edges are sides. Number of sides per face. Like a triangle would have 3 sides.
Oh.
The straws are the edges. Yeah. So we'll do that with, we'll work with the tetrahedron so you know what we're talking about with the pieces. So the tetrahedron has 4 vertices or corners. And the edges refer to these straws that I made. Okay. How many edges, did anybody count their edges on that one? 6, yeah, 6. And the faces would be if we had filled this in with a piece of paper on the edge here. So how many faces were there? 4, yeah, 4 faces. And when we talk about the number of faces per vertex, we mean how many faces meet here. How many triangles meet at the corner? 3 triangles meet, or 3 faces meet at the corner. And then the number of sides per face, the face is the triangle, and there's 3 sides per face.
I think you wrote 1 extra. Let me try to put that on back.
When it turns net, it's not six sides. There's not six sides.
That looks like 620, right? 620? So you're all looking on the computer?
Yeah, I changed it because we don't want the whole
You probably should have put that one back.
Which one do you need?
The one that you put back. Sorry.
No problem.
Thank you.
The cube has four sides.
No, it had 6. Remember it was unfolded there for you?
How about I thought faces?
Faces inside things.
Maybe it was gonna be the same.
Number of sides per face.
Yes.
So you look at one face is a square, and the square has 4 sides.
And the triangle, at one point, they all connect.
I kept losing my spot.
3 faces that is this,
So first side, yeah.
Oh, there are 3 edges on each
So
side.
the question is
3 sides per face.
how many vertices does each side have? Is that also a question? To understand it? Or does it know?
Number of sides per face. So the face has a triangle,
I see where it is.
and the triangle has 3
Fixing it.
faces.
So I have three.
The triangle itself is three vertices.
It does.
So that's the way to look at it.
I don't think so. Will it always have the same number? You know what, it will.
Is it always?
So this, it will have the same number of vertices on the face as it
No, I don't. Keep losing where we started. I know. Too many.
Some of the problem comes in. Yeah, perfect. Some of the problem comes in trying to not miss anything on the bigger ones. So with the 2 bigger ones, the dodecahedron and icosahedron, you can think of there being a top and a bottom. So here's a top pentagon and a bottom pentagon. And then in between the top and bottom, you have either 2 rows of pentagons for the dodecahedron, or the top and bottom here, you have a row of triangles going every other way. So you have the 5 on top and the 5 on the bottom, and then a row going around the middle. Okay, so some of you have it, so let's go ahead and work together. So the cube, how many vertices did the cube have? 8, yeah. So when you hold it, it's you can say, oh, a top 4 and a bottom 4. And how many edges did it have?
12.
12, good. And the number of faces? 6, yes. 6 faces. Number of faces per vertex, we said that already, right? 1, 2, 3. And the number of sides per face, each face is a square, so there's 4 sides per face. The octahedron, has 8 faces. That's why it's called octahedron, for 8. Okay, so there's 4 triangles on the top and 4 triangles on the bottom if you hold it on its point. How many vertices does it have? Yeah, it has 6. So there's a point on the bottom, a point at top, and the 4 around the edge. Number of edges?
8.
It has 12, yeah. So 4 on top, 4 on the bottom, and 4 around the outer edge. Number of faces per vertex. So this is, number of faces was 8. Yeah, we did that. And then number of faces per vertex at each corner, 4 are meeting.
4.
Yeah. And number of sides per face, each face is a triangle. And so 3, yes. The dodecahedron, that's the one that has pentagons. And for me, it's the one that always falls apart in my bag. Okay, so the dodeca, we said, stands for 12. There are 12 faces. You can put 12 for the number of faces. 12 faces. 1 on the top, 1 on the bottom. And if you count around the edges, there's another row of 5 and another row of 5. 12 faces. So how many vertices? Did anybody count the vertices here?
20.
Yeah, good counting. That's not easy. How many edges?
30.
Yeah, good. That's even harder. You got it. How many faces per vertex? Yeah, just 3. 3 pentagons meeting at each corner. So 3 faces per vertex. And the pentagons are the faces, so there's 5 sides for each face. Now the last one that's has the most sides. So Icasa means 20, so there's 20 faces. How many vertices? Who counted the vertices and got it? 12. Good. How many edges? 30. Good counting. There's 20 faces. And if you look at each vertex, there's 5. We already talked about that. There's 5 triangles meeting at each corner. So however you turn it, there's 5 meeting there. And each triangle then has 3 faces. So the number of sides per face is 3. 3 sides per face. So we're quantifying these, and then I'm going to ask you if you see any coincidences or patterns. So can you please spend some time looking at this chart and tell me what coincidences or patterns you see in the chart? You'll want to get this chart right, and it's probably going to be something you want to put on your 3x5 card, because I'll ask you questions about it. I mean, you can bring your platonic solids with you to the quiz, but it's probably easier to write the numbers on the card. I've seen people do both.
The last 2 kind of flip-flop.
Pardon?
I said that.
Okay.
The last 2 kind of flip-flop.
The last 2 flip-flop. Okay, so yeah, you got the 12 over here and the 12 over here, and then you have the 20 over here and the 20 over here. And that happens here as well, doesn't it? 5, 5, and then 3, 3. Good. That's definitely a pattern to observe. What other patterns do you see, or coincidences?
The cube and the octagon do that as well.
The cube and the octagon do that as well. Good. So the cube and the octagon kind of flip-flop their numbers, and so do the dodecahedron and icosahedron. Anybody see any other relationships there? I see a relationship that's missing. When we're counting edges, that's a lot of work. Why can't I just multiply the number of faces, which are easier to count, times the number of sides per face, to get the number of edges? Because that would have been a lot easier than trying to count all those edges. Yes?
The edges can be used to create more than one face.
That's right. The edges can be used to create more than one face. So instead of being able to say 20 faces times 3 edges per face gives me 60, I get 30. 12 faces times 5 edges per face, instead of getting 60, I get 30. 8 faces times 3 edges per face gives me 24, and I get 12. Is anybody seeing a pattern there? It's each edge is used on 2 faces. So this edge is used for one triangle on its left side and one on its right side. And so we could, in fact, the number of faces times the number of edges, and get the number of faces times the number of sides per face, and we get the number of edges times 2. So in other words, if we take the number of faces and multiply times the number of sides per face, we get twice as much as we need, because each edge is used twice. Good. Okay, so each edge is used twice. Well, let's look more at these flip-flopping going on between the cube and the octahedron and the dodecahedron and the icosahedron. That relationship has a name, actually. It's called dualism. So let's start with the cube and the octahedron. The cube and the octahedron are dual. So we can call it duality or dualism. What we mean by that is take your cube and picture yourself inside the cube. In fact, you can do it in the room that you're sitting in here. This is kind of not quite a cube, but picture yourself sitting in a cube and look at the ceiling and put a point on the middle of the ceiling, and then put a point on the middle of the floor, and put a point in the middle of each of the 4 walls around you. Okay, so point on the ceiling, point on the floor, point in the middle of each wall around you.
Well, if you connect all these points together with edges, what shape would you get? So point on the ceiling above your head, point on the floor, point on each of the walls. Connect all of those with edges. Here's somebody trying to imagine it in your book. Connect all those points together. Anybody picture what shape that is? Yeah, exactly. Good. I see you holding it up. Good job. Yep, it's the octahedron. So the octahedron and the cube are dual. You can do the same thing with the octahedron the other way around. Oh, and here's a picture of it. I was going to try and show you mine, but here's a picture. You have a point in the center of each face of the octahedron, and when you connect them, you get a cube. So that's what we mean by duality. If you put a point in the center of each face of the cube and connect them with edges, you get an octahedron. If you put a point in the center of each face of the octahedron and connect those, you get a cube. Same thing happens with the dodecahedron and icosahedron. So that's harder to picture. Your author has a drawing. If you have 3D glasses, then if you take a hardcover of the book with 3D glasses, this looks 3D. So if we put a point in the center of each face of the dodecahedron, you will get those connected with edges and create an icosahedron inside. Well, that means we left one out. Where did my tetrahedron go? Isn't the tetrahedron dual with anything? Can you picture putting a point in the center of each face of the tetrahedron? What would you get if you connected a point in the center of each face of the tetrahedron? Yeah, you would. Good. You get another tetrahedron upside down. So here's another picture in your book for that. So we put a point in the center of each face of the tetrahedron and connect them, and you get another tetrahedron, only upside down. So the tetrahedron is self-dual. The tetrahedron is self-dual. And again, these questions about duality are something I usually ask on quizzes too. So make sure you have those down and understand that. Now, sometimes students wonder, well, where do these show up in real life? Some of the viruses or bacteria are shaped like the platonic solids. And also, I wanted to, well, I guess I'll just mention that if you were storing spheres or other three-dimensional shapes, sometimes when you're storing them, if you put a point in the very center of each shape, like suppose you're shipping cannonballs. Okay, they're all going to roll together in a big bunch in the bottom of your bin, and then the next layer is going to fill in the holes because they're heavy, but they're not going to fill in all the holes. Well, if you put a point in the center of each of those cannonballs at the very center and connect them with edges, you're making platonic solids when you do that. The image you get is platonic solids. So that's another place they show up. I also thought it was interesting. Oh, here's another place. There's some platonic carbons, so sometimes they show up in chemistry, and here's some platonic shaped carbons. But I thought it was interesting that if you take your one with the most sides, your icosahedron, okay, you got it? Everybody picking theirs up. Pick it up. Okay, if you can pick it up and hold the two sides that are diagonal and parallel. So the sides make triangles going up and down. So hold two sides that are going slanted to the back. What you're holding is a golden rectangle. So the golden rectangle shows up in the platonic solids. Here I've tried to break that up a little bit. Here's 3 golden rectangles put together, made out of cardboard. And if I were to connect their edges, rather their corners with string, those would form an icosahedron. So here's a picture of what I did with cardboard, only better. So the strings connecting form an icosahedron. So your golden rectangle, which came about from our Fibonacci numbers, our golden ratio came from the Fibonacci sequence, shows up in the platonic solids. Here in Wikipedia, we have the ordered pairs plotting the points on these 3-dimensional shapes. So in fact, these are the vertices, the corners where you would plot them in 3D. And the cube and the octahedron aren't that interesting, or the tetrahedron. But when you get to the icosahedron, here the ordered pairs are phi, right? And when you look at the dodecahedron, you have phi showing up, and you have the ratio of 1 divided by phi. So the Fibonacci sequence gave us the golden ratio, and the golden ratio shows up in our platonic solids. So I just think that's very interesting. I'm sure I'm forgetting something. Oh, I am, actually. Here. Here I have a clay tetrahedron. My husband made it for me. He's much better at this than me. And now I'm going to wreck it, okay? Who's got a Garrett? Anybody have a Garrett? If you do, we're going to slide away from you carefully and slowly. Okay, no. I don't have one, but that's what works best for cutting clay up. Maybe the art major has a Garrett. No Garrett there. Okay, so let me get a scissors instead. Okay, so I'm going to cut the top off of this. Yeah. So a Garrett's actually a wire, right? Piano wire? Oh. Yeah. That works best with clay. But we'll go ahead and use a scissor. So when I cut the corner off, what shape will be left underneath it?
A triangle.
Yeah, triangle. Okay. So let me do that. Cut the corner off. Okay, so there's a triangle left. I cut it kind of at a slant, so it's not the best triangle. Now I'm going to do that on the other corners as well. When I take away these other 2 triangles, what shape will I have here? What will it be? A what? It won't be another platonic solid. These are going to actually be called truncated platonic solids. So what will the side be here?
I don't remember the section.
How many sides does it have?
Hexagon.
Hexagon, that's right, 6 sides.
It dropped first. I don't remember what it was.
Okay, so we cut off the 3 points. So the truncated tetrahedron gives us a solid that has 6 sides on one face and 3 sides or triangles. So we have hexagons and triangles when we cut off all 4 corners. So the truncated platonic solids are interesting as well. This one is a small, it's a soccer ball, only it's smaller. I actually took it from my dog, poor thing. Okay. It was a worthy sacrifice. She only whimpered a little. All right. Now this has hexagons and pentagons. So the sides of your soccer ball are hexagons and pentagons. So look at your platonic solids and you see which platonic solid is truncated to get this shape. Which one do you cut the corners off and get hexagons and pentagons? So examine yours. So which of your shapes can you get a pentagon and hexagons when you cut off all the corners?
Oh, this one.
Yep, that is the one. Okay, so you take your icosahedron and you see how it has 5 sides meeting together? So if you cut off that corner, you're going to get a 5-sided shape, so that's where the pentagons come from. And you're cutting the corner off triangles. So you cut all the corner off each triangle, that leaves 6-sided shapes. So next time you kick a soccer ball, I hope you think about truncated platonic solids, because that's what you're kicking. There's some other paper ones if you wanted. You could go online and find other paper truncated platonic solids as well. Well, I think that's all we're going to study with platonic solids. I hope you enjoy it. And on Wednesday, we'll take a look at another section. I'll see you then.